All right, our last hydrolysis enzyme. So we had RNase A breaking the phosphodiester bond in RNA. We had lysozyme breaking the glycosidic bond that we had in bacterial carbohydrate cell walls. And now we've got serine proteases. Okay, they're plural, and I'm referring to them as they because it is a class of enzymes that hydrolyze peptide bonds in the GI tract. But the different ones have different specificities for side chains that flank our sessile, our to-be-cleaved peptide bond. But they're all part of this class because they have a common catalytic mechanism with a particularly reactive serine. So I'm going to zoom in here. We're going to see this slide again in just a little bit. But here we can see, here's our substrate polypeptide, and then we've got this specificity pocket that's right next to the bond that's going to be cleaved, and it literally is like a little envelope that you're going to dip in that adjacent side chain, and that's going to determine whether or not this is the right lock enzyme for that key peptide substrate, right? If it doesn't have the match there, it's not a substrate for that specific serine protease. We're also going to talk about here 3 important amino acids that are found right next to one another in the enzyme active site. Look at these numbers too. Amino acid position 57, 102, and 195. These are not close to one another in primary sequence space, but once you fold your protein together, they come together in this perfect, what we call catalytic triad that allows these enzymes to do their chemistry. Okay. Why do we have these enzymes? These serine proteases are important for digesting dietary peptides to allow for them to be broken down into their monomeric form to be taken up from your GI tract. Okay, another enzyme, another protein that's produced in your pancreas, lots that happens in your pancreas. As a precursor or inactive form, we're going to talk about that later on at the very end here, because if you were to make this in an active form, it would actually digest the organ that's making it. That's a problem, okay? So we're going to have them in inactive forms. Largest protein of the ones that we've been studying, not anything you need to know, but what's really interesting is there's only about 40% sequence homology between all of the classes of serine proteases. And the reason for that is, well, you don't need to have too much in common other than having those amino acid residues that form that catalytic triad. Okay, so they all have this catalytic triad. Those are those 3 active site residues, again, with very different primary structure locations, sequence, position locations, but their tertiary structure is going to position them all in the same spot so that these enzymes have the same function. All right. As we've done with all of these, let's start by looking at the uncatalyzed reaction, seeing what happens, and then understanding how we're going to map on amino acid side chains to do that chemistry. So here's our NC-alpha-carbonyl, our little peptide bond, right? We've got our side chains that we have here. Here's the bond that we're talking about cleaving. That's our sessile bond. Okay? When we think about what happens mechanistically, right? We've got water that's going to come in, nucleophilically attack this amide carbonyl. We're going to generate a tetrahedral intermediate. Remember, 2 options for tetrahedral intermediates. You can decompose them if you've got something else that could be a good leaving group, or you might have to protonate them. That was the case if you had aldehydes or ketones. Now we actually have a functional group that has a decent leaving group. We make leaving groups be better leaving groups by protonating them. So this tetrahedral intermediate can decompose, protonate our leaving group, and we end up with our cleaved polypeptide. Okay, here this is going to be our upstream, or what we call our N-terminal peptide, because it is the one that has the N-terminus to it, and then our downstream or C-terminal peptide. Okay, we also could facilitate this chemistry by having a base deprotonate our incoming water nucleophile. That's going to make it more nucleophilic. So again, seeing places where we've got acid or base doing chemistry, we can map on amino acids to help with that chemistry. All right, remembering our 3 steps here, we need to have chemistry on the substrate, we need to use all our reagents, and we need to regenerate our enzyme active site. Well, what if, rather than thinking about using water in terms of using all of our reagents, what if we used serine? Do you remember we talked about sometimes we can have amino acid residues that can serve as surrogates for other molecules. So things like serine and threonine are able to serve as surrogates for water. I'm going to be activating SIRI here in a minute. Okay, so let's map on what would happen if this wasn't water, but rather it was serine. Okay, nucleophilic attack, generation of a tetrahedral intermediate is not going to be a free hydroxyl there. It'll be hydroxyl that's connected to serine that's part of our enzyme active site. Rest of the chemistry is going to continue as we'd seen before. Decomposition of our tetrahedral intermediate, protonation of our leaving group is now going to generate our cleaved polypeptide, but now rather than being a fully cleaved polypeptide, we're going to have this serine that is connected to our N-terminal portion of our peptide. Okay, so this is not going to be able to leave the enzyme active site at this point because it's covalently bonded to it, but our downstream, our C-terminal peptide can. So as a heads up, this is where this is going. What we're going to see is that water is now going to come into the enzyme active site. Water is going to liberate this N-terminal portion of our peptide from our protein, and we're going to then free up that amino acid residue to continue to do chemistry. Okay, so places that we can sort of map stuff on here, we've got, places where we could have general acids help, we could have general bases help, okay? So this is where that catalytic triad is going to come in. So let me zoom in here just for a second because there's two things I want to talk about before we move on and sort of talk about the details of the enzyme active site, okay? So remember, here's this catalytic triad. We've highlighted that this serine residue is going to act as a nucleophile. And one of the things that we're going to see is the histidine that's adjacent to it is going to deprotonate it. It's going to make it be a better nucleophile. And the aspartic acid that's adjacent to it is going to make it be a better base because it's going to donate electron density by electrostatic catalysis. Okay, so that's what we're going to see with our catalytic triad. But before we get into that, I want to talk just for a second about this specificity pocket. Okay. I do want you to know names that we sort of have for that. Oh, we sort of talked about this, but let's summarize this here, this catalytic triad. So again, we've got this reactive serine residue. Okay, that reactive serine residue is going to perform nucleophilic catalysis. So it's a nucleophilic catalyst. It's going to be forming a covalent bond with our substrate. This essential histidine residue is going to be a general base catalyst. And its role is to deprotonate.
Okay,
I
found it.
It's going to deprotonate our serine. And that solvent inaccessible aspartic acid is going to be electrostatic catalyst. So it's going to make histidine be a better base. So these work sort of like the Three Musketeers, if you will. We've got aspartic acid that's making histidine be a better base. Histidine as a base is going to deprotonate serine, and then serine goes and does its chemistry. Okay, so let's talk just briefly about substrate specificity. So I'm going to flip back to this picture just for a second to remind you, since I went to talk about the catalytic triad here. Oh, this. So let me zoom in here. When we look at what's happening here, I want you to see this. Think about this as like being like a little hanging pocket that we have there. And amino acids that are immediately adjacent to the bond that's going to be cleaved, that peptide bond that we're cleaving, have the ability to kind of like nestle in there and sort of sample that little space. And depending on whether we have favorable or unfavorable interactions will determine whether it sticks around and stays. Okay, so names that I want you to know: chymotrypsin. So chymotrypsin is the serine protease that will cleave next to phenylalanine, tryptophan, or tyrosine residues. You thought so. Okay.
Okay.
This is going to be a rough video because of the name of that amino acid. Okay, so what happens if we look at the enzyme active site? Okay, and we look at that substrate binding pocket, we've got kind of, it doesn't really show it here, but it's kind of slit-like. It's almost like an envelope pocket, okay? And what's gonna happen when you have those aromatic residues that are flat, they're gonna be able to slide in there nicely, form some nice intermolecular forces. It's gonna be a match, and then that enzyme is going to do its protease chemistry. Okay, let's look at trypsin. Trypsin is going to cleave after lysine and arginine residues. Okay, so if we look at that substrate binding pocket, a fairly deep pocket, and then down in the bottom, it has a negatively charged residue. Ooh, that's going to form favorable interactions with something that has a positive charge. So something like that protonated amine at the end of lysine, or that arginine group is also going to have a protonated group, that guanidino group that we have there. Elastase, this is kind of the most interesting one. Elastase has a fairly shallow pocket that's sort of filled. And the idea is if you are too big and you try to dip your side chain into that pocket, not going to work, and you're not going to be able to bind, and you are not a substrate for that enzyme. If you are a small nonpolar residue, though, you're going to be able to kind of get in there, okay? I should say small neutral residue. You're going to be able to get in there. So this is almost that baseball and basketball analogy again. Why would this substrate not be able to bind into the active sites for these other guys? Well, remember, if we're putting this guy in where it cannot form these favorable interactions, okay, the slit-like pocket with chymotrypsin, or that positive-negative electrostatic interaction with trypsin, it's not going to be compensated for. So it doesn't hang around long enough in that substrate binding pocket to have chemistry happen. Okay, so let's look at this enzyme active site. Okay, this is the most involved enzyme active site, but a lot of steps to it. But I hope you see that there's a repeated pattern. There's still this Act 1 and Act 2. Act 1 does chemistry on the substrate. Act 2 involves water and regenerates the enzyme active site. Okay, so let's kind of start up here. We've got our substrate polypeptide shown very generically here. All we're really showing is that peptide bond that's going to be cleaved. Here's our catalytic triad, right? They don't show that we've got some side chain that's over here that's fitting positively into that substrate binding pocket to allow us to say this is a match between this substrate and this enzyme. So catalytic triad is all going to help serine 195 do its chemistry. Okay, so serine 195, if we kind of label what's going on here, serine 195, okay, forms a covalent bond with our substrate polypeptide.
I found this on.
Oh, let me start over here again. Serine 195 forms a covalent bond with the substrate polypeptide via covalent catalysis. How do I stop this? What do I? Okay. That amino acid, this amino acid's reactivity is enhanced by histidine 57 acting as a general base catalyst. Its basicity is enhanced by aspartic acid 102 acting via electrostatic catalysis. And these represent the catalytic triad. Okay? We're going to see this on the next slide. Okay? But I want to give you a highlight for it because it's not sort of all written in here. This right now, this carbon atom is sp2 hybridized. Let's actually write it in here. This guy is sp2 hybridized, so it is planar. And it's also neutral in terms of its charge. Once we do this chemistry and we generate a tetrahedral intermediate, okay, this tetrahedral intermediate is now sp3 hybridized and it's negatively charged. Okay, so one of the things that we're going to highlight is we've got this thing right here. We have created a negative charge on that oxygen and we've changed the geometry such that we've pushed it into a different spot. And why this is important is this is now pushing into something that we call the oxyanion hole. Okay, so we formed a tetrahedral intermediate. And we talked about what happens with tetrahedral intermediates Has to do with one of two things, and it depends on what it's connected to. We can either protonate that tetrahedral intermediate if we have something that doesn't have a good leaving group. But in this case, we do have something that could be a good leaving group here, especially if protonated. And so we are going to decompose this tetrahedral intermediate. We are going to break this peptide bond, and the departure of this N-terminal peptide is going to be facilitated by protonation of it as a leaving group. Okay, so said another way, this reaction is going to proceed toward product by decomposing this tetrahedral intermediate, by cleaving the peptide bond, okay, and forming what we call an acyl enzyme intermediate. Remember, we said that that serine is going to be connected to our substrate. So we've got an acyl enzyme intermediate. This is again facilitated by general acid catalysis by histidine 57. Okay, so here we've got histidine 57 now acting as a general acid catalyst to protonate that N-terminal peptide and make it a better leaving group. Okay, so now what's going to happen is this N-terminal peptide is going to diffuse out, water can diffuse in, and seen. Okay, now we've got the end of Act 1. Remember we talked about what happens in Act 1? Chemistry on the substrate. We've cleaved that peptide bond, but we haven't yet involved water, and truthfully, our enzyme active site is not back in its proper state. Even though that histidine and part of the catalytic triad is back where it's supposed to be, we still have half of our substrate covalently attached to our enzyme. That's a problem. So what we're really going to see here in Act 2 is really a redo of Act 1, but now with a different nucleophile as our player. Okay, so let's come over here. Water has diffused into the enzyme active site. Now we're ready to continue. Okay, we've got our catalytic triad, or at least the dyad portion of it, ready to do its chemistry. So histidine 57, acting as a base catalyst, deprotonates water, increasing its nucleophilicity towards attack on the carbonyl carbon of our acyl enzyme intermediate, forming a tetrahedral intermediate. I'm going to highlight here that we're going to have stabilization of this tetrahedral intermediate by that same oxyanion hole. Now we're going to see decomposition of this tetrahedral intermediate. Now notice here, if we broke this bond to the tetrahedral intermediate, we would just go backwards. Same thing up here, right? When this tetrahedral intermediate decomposed, sure, we could break that bond, but that's not moving towards product. This is the bond that's moving towards product and breaking that peptide bond. All right, so coming back down here, decomposing this tetrahedral intermediate, breaking that bond, that acyl enzyme bond. Okay, that's going to be facilitated by histidine 57 acting as a general acid. Okay, and ultimately, when we're all done with this chemistry, that C-terminal peptide can diffuse away from the enzyme active site, and everybody has been regenerated in their active state. Okay, so you'll notice that histidine actually went through its deprotonation, protonation.
I didn't get that. Could you?
Histidine actually went through its deprotonation, protonation, deprotonation, protonation. Went through that twice, okay? Serine only went through its stuff once, right? So it only served as a nucleophile once. Wow, that's a lot. These enzyme active sites, it's a lot, okay? The last little piece here, there's actually two little pieces here. I want to highlight that when we have the generation of that sp3, that tetrahedral intermediate, what we're going to have is the ability to stabilize that, okay? And that's through what we call the oxyanion hole. So let's kind of reorient ourselves. Here's our substrate polypeptide. Here's our peptide bond. Here is the amino acid that's immediately adjacent to the bond that's to be cleaved. So this is kind of sitting in our substrate binding pocket. So that's determining that that's a match with that substrate for that enzyme. Here's our catalytic triad. Catalytically reactive serine, there's its OH group. Our histidine, ready to act as a general base. And then our aspartic acid, ready to help increase that basicity. Oh, this is bad.
I didn't get that. Could you try again?
Okay, so watch what happens here. I'm going to map on what we had on our previous slide. This is sp2 hybridized. It's planar, and it's uncharged. When we form our tetrahedral intermediate, this guy now becomes sp3 hybridized. It's tetrahedral in its geometry, and it becomes anionic. So how that is stabilized is by this oxyanion hole. Okay, so what is in that oxyanion hole? Okay, we're going to have negative stuff that gets thrown in there. And so we're going to have backbone atoms that can hydrogen bond there and help stabilize that negative charge. Okay, so that helps make the formation of that tetrahedral intermediate much more favorable because it's stabilizing us getting there. All right, so this kind of like flips back and forth. It's a little bit hard to see when I'm trying to flip here. Let's see if I can do it quickly here. When I kind of flip back and forth, actually works better if you're toggling kind of on a PowerPoint where it just instantly flips rather than swipes. Okay, but we can see that that's helping to stabilize that transition state, leading to that tetrahedral intermediate. Okay, last little piece here, okay? Thinking about how you don't eat your own internal organs because you are making enzymes that are designed to eat protein, okay? You make them in a precursor form. Anytime we see the word pro in front of an enzyme or a protein, that refers to that enzyme or protein in an inactive form. We talked about that with proinsulin. Proinsulin is insulin in an inactive precursor form. Remember that C peptide is there, and the purpose of that C peptide is to hold that A chain and B chain in the right orientation for the right disulfide lengths to make active insulin. Okay, we don't have exactly the same situation here, but we do have inactive precursor forms of these digestive enzymes. Here's how most of them work. They are actually going to have a N-terminal portion that's extra, a little tag on the front end of the protein. And why this is important is when it's there and the protein folds, it doesn't create the catalytic triad, so it can't do its chemistry. So what happens though is if you snip off these little 15 amino acid residue pieces, then all of a sudden you can rearrange, you can shift, and you become active because you created that catalytic triad. So here's the interesting story of how you do this cleavage and how this happens. Okay, so this is what we call trypsinogen. And I know we don't just call it protrypsin. That would be too easy. These are what we call zymogens. That's a name I want you to know. So zymogens are the precursor or the proenzymes of these proteolytic enzymes. So trypsinogen is the proenzyme or the zymogen of trypsin. Remember what trypsin cleaves after. Trypsin cleaves after positively charged residues like lysine and arginine. Okay, so what's going to happen is you've got this inactive precursor form that gets squirted into your GI tract. In your GI tract, there's already active trypsin or other peptidases that are going to cleave off this N-terminal tag, and then you're left with this active protein refolded and able to do its digestive chemistry. This, however, is why kind of acute trauma to your abdomen can be problematic. If anything happens where you sort of release any of your digestive juices on your internal organs, particularly your pancreas, it's going to activate those proteolytic enzymes, and they're going to start digesting your internal organs like they were your lunch. So that's a problem, okay? So, and I really didn't talk about this in class, what this picture is. This is a picture showing this is trypsin. So let's kind of label this here. This guy in red here is trypsin. So that's the enzyme responsible for doing that protein digestion. And this guy in green here is what we call BPTI, bovine pancreatic trypsin inhibitor. It's basically what we call a suicide inhibitor. It's a molecule that binds so strongly to its enzyme that it completely inactivates it. So you actually have little bits of this that are sort of floating around in your body in case there happened to be any rogue trypsin that happened to get out of a place it was supposed to be. It'll lock onto and inhibit it so that it can't do that digestive chemistry outside of your GI tract. Wow, that was a lot. My voice is done for today, but that's everything that we need to know about our enzymes. And this video is specifically on serine proteases.